Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi ta'ala wabarakatuh. Alhamdulillah, now we are going to the second part of the angle modulation, which is how do we plot the spectrum of angle modulated signal. Alright, so for previous lesson, we have learned about how to do modulated signal for frequency and phase modulation. Okay, as we know, there will be the frequency part and also the phase part. So now we are going to analyze how we do the spectrum of an angle modulated. So when we plot this angle modulated signal in exponential form, we will have this kind of function, which is RE E J 2 pi FCT from the first part of the cos, and then EJ beta sine 2 pi FMT. Right, so we are going to have this as an envelope and this one as an exponential. So this complex envelope show that it is a periodic with an exponential form with the period values of 1 over Fm. Okay, so since this is periodic, we can do a complex Fourier series. So it's equivalent to the summation of Cn E J 2 pi n FMT. Okay, so if you can recall, how do we change a signal to a Fourier series? By multiplying that signal with E J 2 pi n FT, and there is a constant. Okay, so to further explain this equation, we will say that this kind of equation will be defined as the Bessel function. Okay, what is Bessel function? Basically, this is the graph of Bessel function or the plots of Bessel function. From this Bessel function, it shows that it looks like an exponential here, but there is also the periodic signal of the function itself. Okay, so this is equivalent to EJ power of 2 pi n FMT. Okay, so the plot is dependable on the modulation index beta. Okay, so for example, if we see at beta equivalent to 1, okay, when we cross out these plots, the one that affected is, there are few places, about 5, 1, 0.765, number 2, 0.440 here. The next one is 0.115, 0.02, and one more 0.002. Okay, so that's mean if we got an modulation index equivalent to 1, which is beta, these are the spectrum or magnitude of the sidebar that we are going to plot. The first one, okay, the first one is usually or representing the carrier magnitude or amplitude of the carrier. Alright, so let's see other values. For example, this one we have different beta values. So what is beta? Just to refresh, beta is the maximum frequency deviation divided by the modulating frequency. Okay, beta equal to delta F max divided by Fm. Right. So going back to the Bessel function just now, so we see that the spectrum of the Fm will not only contain the carrier, but also the content of the carrier is at n equal to 0, but the component or side bands are located at n not equal to 0, means 1, 2, 3, 4, 5 until infinity, right? It will be multiples of the signal frequency. Okay, let's say we want to substitute this one. So the sideband will be at the FC plus 1 FM, minus 1 FM, plus 2 FM, and also minus 2 FM. And until the magnitude become negligible or zero. Okay, so how does that happen? This is because the magnitude of the sideband, okay, will become negligible for sufficiently large n or very big n. Okay, so if you can see here at J0, the value is, we can read it here very clear. And J1, J2, J3, J4, until here, the value will be decaying until n equal to very large or negligible. Okay. Alright, so when we plot this sideband, okay, the sideband will contain an energy. So this energy will be transmitted to bring the information that we are sending. Okay. So it will account at least 98% power of this FM signal. Okay. Of course, this beta plus 1 is the number of sideband and also carrier. Okay, so the beta is depending on the sideband, and plus 1 is the carrier. Okay, so how do we find this maximum power or almost maximum power or almost 98% power bandwidth? Is by measuring the beta and also the FM. Okay, how we find the maximum bandwidth? By using the frequency 2 multiplied by beta plus 1 multiplied by FM. Or if you want to substitute beta, which is equivalent to delta F max divided by FM, we can also use total bandwidth equivalent to 2 multiplied by delta F max plus FM. Okay, the same. Alright, so let's take a look again to this table. This is the values of the Bessel function. These values are extracted from this graph. Okay, so for example, we can extract beta equivalent to 0.1, 0.2, beta equal to 1, 2, 3 until any numbers. Okay, so at each numbers, we will identify what is the value at each function or plots. Okay, just now I show the beta equivalent to 1. So let's take a look of this one. Beta equivalent to 5, that means you will have 1, 2, 3, 4, 11 set of values left and right. That means 10 on the right and 10 on the left. Okay, so for example, beta equivalent to 2, that means here, okay, beta equivalent to 2, you will have 1, 2, 3, 4, 5, 6, 7, including the carrier. Okay, so beta equivalent to 2 is the first one, 0.224 here, the carrier 0.2. Then the next one is 0.57, which is this one. They just put 2 decimal for 57, left and right, plus and minus. So the first one is FC, the second one is FC plus FM. To the right, okay, to the left, FC minus FM. Okay, so this is the first multiple, and the second multiple, if you see in the table, 0.353. 0.353, you put into 2 decimal number. That means the second multiple. This is the first multiple, the second multiple, and then the third and the fourth. Okay, we take to the third and the fourth. Okay, so this one are very small, 0.007 and 0.001, which is here and here. So that's why it was saying that 98% of the bandwidth is occupied here. So the rest is ignored because the magnitude is very low, right? Okay, so this is also some of the magnitude spectra for different values of beta. Okay, so for different values of beta, beta equal to 1. Okay, just now we'll see beta equal to 1. So we have 1, 2, 3, 4 sideband. Okay, 1, 2, 3, 4. This very small one is negligible because it only count the. But if you want to plot in the exam, like you're not sure whether we should plot this or not, you can just plot, but very almost 0, 0.002. Okay, this one 0.02. Okay, I think this is they put the marks for you. So after that is negligible. Okay, all right. So how to find the total bandwidth in summary for a sinusoidal modulating signal. For a sinusoidal modulating signal, usually we have known the Fm. So we also know the delta F max. So you can find the total bandwidth by 2 multiplied by delta F max plus Fm for frequency modulated. And for phase modulated, we can measure the total bandwidth as 2 multiplied by delta max plus 1. Okay. Also dependable on the frequency of the modulating signal. Okay, so this is known as Carson's rule, where it says that Carson said the bandwidth required to transmit an angle modulated wave, which is FM and PM, is equivalent to twice the sum of the maximum deviation, twice the sum of maximum deviation and the modulating signal frequency. Okay, so 2 multiplied by this one plus 1 and plus each this one and multiplied by 2. Okay. Alright, so if we have a signal, arbitrary message signal, known bandwidth, okay, for example, just now we don't know the bandwidth, but we know the frequency of the modulating signal. We will define the deviation ratio as the peak frequency deviation divided by bandwidth of the message signal. So this arbitrary message signal, usually we know the bandwidth and the information of the FM is not known. Okay, so what is the difference of D and beta? Okay, so actually it's more or less the same. It plays the same role as modulation index. But this one, if you know the B, so we calculate the deviation ratio. If you know the FM, we can calculate the beta, the modulation index, the same. So D and B plays the same role to determine the bandwidth. Okay, so if we are given B, so we can have the deviation ratio by multiplying 2 multiplied by D plus 1 multiplied with the bandwidth of the modulating signal. Okay, so we can have the total bandwidth, or delta F max plus the bandwidth multiplied by 2. Also, we can get the total bandwidth of the frequency modulated signal. And for PM, we can also have the maximum phase deviation plus 1 multiplied by the bandwidth and 2. Okay, double. Alright. So this is for how you find the total bandwidth given to you the bandwidth of the modulating signal. Alright. Okay, just now 2 delta F max plus Fm, and here also Fm. Okay, but this one is the B, the bandwidth of the modulating signal. But what is the difference of this one? This is the total bandwidth. Okay, after we do the modulated signal. Alright, so let's see this example. We calculate the bandwidth of the FM signal, means that we want to know what is the total bandwidth. Alright, so usually the FM radio are transmitting from 88 to 108 megahertz. Okay, the bandwidth of the information, Okay, like for example, one channel is 15 kilohertz. And using the frequency modulated signal, we set the peak frequency deviation is 75 kilohertz. So we want to know what is the bandwidth or total bandwidth of this FM signal. So we know the signal of the bandwidth of the signal is 15, maximum deviation is 75 kilohertz. So we can calculate the deviation ratio, right? So here they didn't say modulating frequency, but it say the bandwidth. Okay, so we are using the second formula to find the total bandwidth. Okay, so we identify deviation ratio of 5. We know the bandwidth is 15, okay, plus 75 multiplied by 2, we got 108 kilohertz. Okay, all right, let's see the next example. Let's say we have, this is already modulated for you, an angle modulated signal equivalent to 10 cos 2 pi 10 t. So this is the FC, and plus 2. 2 is the beta, sine 4 pi multiplied by 10 to the power of 3t is the signal. Okay. Determine the phase deviation, frequency deviation, average power, and also asking for is this a frequency or phase modulated signal. Alright, so let's take a look at this equation. When we assume this is a phase modulated signal, because we want to know the peak phase deviation, so we see this part. Okay, this is the one that differ from FM and PM. Okay, so when we identify this is PM, so this is the peak phase deviation, which is 2 radians. Alright, so if you want to say that this is a FM modulated signal, okay, so what we will have to do is we have to find where is this peak frequency deviation located. Okay, so we can find the peak frequency deviation when we find the intermediate frequency. Okay, Fi. Okay, so Fi is equivalent to Fc plus Kf max St multiplied by Snt, or Fc plus delta F max plus Snt. Okay, so we differentiate the phase, which is 2 pi multiplied by 10 to the power 10t plus 2 sine 4 pi t. So we get this one. So this is the Fc, and this is the maximum frequency deviation. Okay, so this is the original message SNT, or normalized signal. Alright. Okay, so next is how we calculate the power. The power in modulated signal. We cover this in previous this chapter, but in part 1, where the average power we just calculate AC squared divided by 2. What is AC? Is the amplitude of the carrier. So we can find the amplitude of the carrier here. Okay, this is AC. Okay, so we just take AC squared divided by 2 is equivalent to the average power. Alright, so this is a revision whether the signal is a frequency or phase modulated, so it can be both. Okay, it's a PM signal in the previous example with a peak phase deviation of 2 radians, and it's also an FM since we have derived the phase and get the maximum frequency of 4 times 10 to the power of 3. Okay, talking about peak and maximum is the same. Okay, so when we are talking about peak frequency deviation, is actually a maximum frequency deviation. Alright, so let's see this example 5.4 in the books. Consider an FM signal modulating a 10 megahertz carrier. Okay, 10 megahertz carrier with a 1 kilohertz sinusoidal waveform. Okay, so the FM is 1 kilohertz, FC is 10 megahertz, and the frequency deviation, maximum frequency deviation or delta F max is 2.5 kilohertz. Okay, determine the bandwidth of the modulated signal. This one is using formula, the Carson's formula. The second one, if the modulating signal amplitude is double, determine the bandwidth of the modulated signal. Okay, so they want to see if we double the amplitude, is the bandwidth is changed, right? So we can see from the equation, is the amplitude is related in the equation to find the total bandwidth. Okay. Number C, the bandwidth of the modulated signal. If is it changed? We given that the signal frequency FM is double. So this one we can expect it will change because the FM is there in the equation. Okay. The next one, determine the bandwidth of the modulated signal if both frequency and amplitude is changed to double. Okay. Okay, so for the first one, determine the bandwidth. This one is using the Carson formula. Delta F max plus FM multiplied by 2. So we know FM 1 kilohertz. Peak or maximum frequency deviation is 2.5. So the total 2.5 plus 3 multiplied by 2 is 7. Okay. Now the question is, we double the amplitude. Okay. Is the total bandwidth become double? So doubling the amplitude will double the peak frequency delta F max, because this is the location of the AM, doubling the amplitude, right, signal. Okay, so KF will be AM multiplied by 2. Okay, so now delta F max previously is 2.5. Now multiplied by 2, we assume AM is equal to 1, so it just multiplied by 2, so 2.5 times 2 is 5. Okay, so 5 plus 5 plus 1, so if we change the amplitude, the total bandwidth will change. Alright, how about the modulating signal is double? So previously is 1, now become 2. Okay, so the total bandwidth will also change. Previously 7 is now 9. Okay, here this is the FM. Sorry, here. Okay, and then if both change, of course, the total bandwidth will be changed also. Right. Okay, let's see the next example. For example, we have a sinusoidal signal sine 2 pi 1000t. Say 1000 is the FM. Okay. And the carrier is 500,000 FC. Okay. The maximum frequency deviation is 1 kilohertz. Find the modulation index beta. So delta F max divided by FM, we can get the beta. Okay. The number of sets of significant side frequency, this one you can get by finding the beta. So you can refer to the table. How many set of significant frequency? Okay, after you get this one, you can draw the spectrum, right? And then determine the bandwidth for the angle modulated is you find the total bandwidth BT. Okay, FC 500, FM 1 kilohertz. Now we find the modulation index beta. Delta F max divided by FM. Delta F max 1K, FM 1000, 1000 divided by 1000 equivalent to 1. Okay, now we have the beta equivalent to 1. So from the Bessel table, if beta equivalent to 1, the side will be J1, J2, J3, and J4. The first one is the carrier. This one is the amplitude of the carrier. So this is the sideband at plus and minus, okay, FC. Yeah. Okay, so this one is the carrier. This one is the sideband 1, 2, 3, 4. Okay, so the total bandwidth, if we using this Bessel function, is N is the number of sideband 1, 2, 3, 4 multiplied by the FM is the modulating frequency. So the total bandwidth, if we are using this table, is 8 kilohertz. Okay, so if you can see FM, FC is 500. So this is 500 FC. Okay. And FC plus FM, FM is 1000. So the next is 501. FC minus FM, 499. FC plus 2FM. FC 500 plus 2FM, 2000. So 502 and plus 3FM here plus 4FM. Okay. So that is how we plot the frequency spectrum of FM signal. So the amplitude is referring to the Bessel function table. Alright. So the location of the FC is the first Bessel table, and then the sidebar is the next FM values. Right, so the question D, determine the bandwidth for the angle modulated wave by using table. We done already just now. N is the sideband 4 multiplied by 1 kilohertz is the FM multiplied by 2, 8 kilohertz. Alright, but if you are using the Carson's rule, it says that the Carson's rules, it double the maximum deviation, summation of the maximum deviation and the modulating signal. So it only give you 4 kilohertz, the total bandwidth. Okay, so usually Carson's rule gives an approximation, and which is lesser than this one. Okay, the one with table, Bessel table. Okay. The next one is, what is this different question. What is the maximum bandwidth or BT of an FM signal where it has maximum deviation of 30 kilohertz and modulating signal of 5 kilohertz. Okay. If you want to use the table of Bessel function and how we find the total bandwidth using Carson's rule. Okay, first of all, we have to find the beta. What is beta? The modulation index, which is the formula peak frequency deviation divided by FM modulating frequency. So beta is equivalent to 6. Okay, so this is table, Bessel function table. At beta or modulation index equal to 6, we have the first amplitude of the carrier is 0.15, and 1, 2, 3, 4, 5, 6, 7 until 9, there will be the sideband. Okay, so using Bessel formula table, so we have 9 set of Bessel function multiplied by FM. 945 times 2, 90 kilohertz, but using Carson's rules, we got these values, which is also smaller than the Bessel table. So if you want to plot, the first one, 0.15 is the carrier. Okay, the first one, this is the carrier. The next one is the sideband, 9 on the right plus and on the left. Okay, so this is the bandwidth using Bessel functions and Carson's rule. Right, so it's already 30 minutes, so I'll stop here. If you have questions, you can just PM me or text here. Alright, so with that, I end the lecture with Mukitab and Farah. Thank you very much.